Okay, continuing on with number 17. Here I want to find the equivalent resistance and the currents and voltages on each of these resistors. So first of all, let's just find the equivalent of this. That's going to be 1 over 2 plus 1 over 2. That's equal to 1. So I can replace these two resistors with just a 1 ohm resistor. Right? And then I can find the equivalent of this. That's going to be 3. And then the equivalent of this 1 and 5 will be 6. So let's just redraw this. I have a 2 ohm there, a 3 ohm, and a 6 ohm. So this is 3 ohms, 6 ohms, and then this is 2 ohms. A 3 and a 6 together give me 2 ohms. That's 1 over 3 plus 1 over 6 is 1 over a half, and that's equal to 2. So if I redraw this again, I get a 2 ohm and a 2 ohm. This is 12 volts. And then so the equivalent then is going to be equal to 4 ohms. That's just 2 plus 2. Okay, so now I can start assigning some voltages. I know that I have 6 volts here and 6 volts here. Okay, that is 6 volts here, which is the same as what I have here. And since these two are in parallel, they're both going to have 6 volts and 6 volts. Okay, now here I'm going to have a current equal to V over R, the 6 over 3, or 2 amps. So that means that I have 2 amps going through each of these. So R2 and R3 are both going to have 2 amps. All right. I've already said that R1 has 6 volts. Now R4 has 6 volts here, or rather on this 6 ohm resistor I have 6 volts. I have an equivalent of 6 ohms. That means I'm going to have 1 amp. So I have 1 amp coming into this portion of the circuit. Let's clean this up a little bit. I have 1 amp coming into that portion of the circuit. These are two identical resistors, so they're both going to get 0.5 amps. Right, so R4 and R5 both get 0.5 amps, 0.5 amps, and then R6 is going to get 1 amp. All right, so now I can go back and figure out the missing values. So for R1, I is going to be 6 over 2, that's 3 amps. And notice here that I get 3 amps coming in, and it splits into 2 amps and 1 amp. So that's a good check. That is to check your answer. And now R2 was 2 ohms. V is going to equal I times R. 2 ohms times 2 amps is 4 volts. 1 ohm times 2 amps is 2 amps. Notice these need to add up to equal 6 volts, as they do, 2 plus 4. R4 and R5 both have 1 volt. And R6 has IR, are 5 volts. So our RC circuit, how long with these dimensions, how long is the capacitor required to fully charge? Well, for 1 tau is equal to RC. That's equal to 4 megohms times 2 microfarads. That's equal to 8 seconds. And so the total time is 10 times tau, which is 80 seconds. So that's the answer to part A, or part 1. What is the charge on the capacitor after 8 seconds? All right, well, the charge, Q, is equal to Q, big Q, 1 minus e to the minus t over RC. Q is equal to CV. T is 8 seconds. Our time constant was also 8 seconds, so that makes it easy. Let's see, CV. C is 2 microfarads, 10 volts. This is what, 0.63, I think. Yeah, 0.63. So that's 20 times 0.63. You get negative 12 13.6, or excuse me, 12.6. We'll just call it 13 microcoulombs. So that's the charge after 8 seconds. And then sketch a plot of the charge versus time. So 3, the charge versus the time looks like this, and it's going to asymptote to that maximum value of Q equals 20 microcoulombs. So at T equal 8 seconds, it was roughly like right here at 13 microcoulombs. All right. Now remove the battery from the circuit, and now it's discharging. What is the current through the circuit at T equals 16 seconds? Or my current, let's do B first. My current is going to look I versus T. It'll start here, and it's going to go down. It'll eventually go down to 0. It's going to start at V over R. That's the maximum current. Now, this is given by this function. So V was 10 volts over 4 times 10 to the 6 ohms. E to the minus, was it 16 seconds? 16 seconds over 8 seconds. Times 0.14. I get 3.4 times 10 to the minus 7 amps. That's the answer. And this is the plot for the second part of that. All right, I think there's just one more, or a couple more. What must be the maximum allowed current in the circuit breaker to accommodate all of these electrical devices? Well, they all operate at 120 volts. And so P equals VI. So I want to find the current for each. That's going to be P over V. So 100, this is the current, then I'll just have another column here, is 100 over 120. And that's going to equal 0.83. I'll just call it 0.8. This is going to be 40 over 120. 0.3. 500 over 120. That's equal to 4. 1,000 over 120. That's equal to 8. 300 over 120. 2.5, or you might round it up to 3. That would be fine. I get 6.7. And then if I add all those up, I get the total current. Let's see here. 2 carry. Oh no, let's see. This was 0.8, 0.3. Well, let me just do it in my calculator. Hold on. Okay, so 0.8, 0.3, 4, 8, 2.5, 6.7. I get 22.3. If I add up all these currents, 22.3 amps, or 22 amps. So you need a circuit breaker that was about 25 amps or so. All right, describing 25 watts or less, how a gram fault circuit interrupts the GFCI. Turns off, or let's say it monitors I in and I out. It turns off if I in ever exceeds I out. That's enough. How many words is that? 1, 2, 3, 4, 5, 6, 7, 8. 13 words. Okay, it's very simple. I'm just looking for this, basically, that it turns off if the input current exceeds the output current. I think that's all. There's the multiple choice answers. We'll stop.